Let's prove this result in the geometry of Desargues. So if point P is on the polar of Q, say I'm going to say suppose this is point Q, and P, this line is the polar of Q, and P is on it. We want to show that point Q is on the polar of P. Now, I would advise you to review the definition of polar. When P is on the polar of Q, that means no points on this polar will be lying on the same line connecting Q. That means P and Q should not be on the same line. Any points on the polar should not be on the same line as on the line that passing through the Q. So I would like to write this down, and P and Q can be on the same line. On the same line by definition. Please review the definition if needed. Definition. And now I would like to approach this problem using the proof by contradiction. So I will assume this is not true. This means Q is not on the polar of point P, and then we try to reach to a contradiction. For the convenience purpose, I'm gonna say I'm gonna call this M as the polar of point Q. Okay, and then say I'm gonna say suppose Q is not on the polar of point P, which is the negation of this to be proved statement. So I need to give a name for this polar of P. So let's say L be the polar of P. So in other words, I'm going to call this as my line L, which is the polar of P. And obviously, what we are saying here, Q is not on this polar. That means Q is not on this L, right? I.e., then Q is not on L. Okay, this is just by assumption, right? By assumption. Well, we go back to that definition again, because Q is not on this line L, and then this line is the polar of P. That means no line through P will intersect L. So there's no line connecting P and any points on the L, right? That means no line will be connecting P and intersecting the L. Okay, so I'm going to write this down, and oops, and no line through P can intersect this line L. This is really just by definition of polar, because that's the polar of P. What I'm trying to establish is therefore M and L do not intersect, because no line connecting P will be intersecting the any points there, right? Okay, now let's take a look at axiom 6, which is right there. So let's read through that. If a line does not contain a point, a certain point, so do you see that L doesn't contain the Q in this case, okay? Then there exists a point on both the line and any point and any polar of the point. Okay. In other words, there should be a line, a point. There should be a point on both this line, so on this line, so this line, and the polar of the certain points. The polar, which is this polar, right? The polar of this Q is this guy. So there should be a point on both this line and the polar. That means these two must intersect, right? That's what this A6 says. So therefore by A6, the line L, which is the polar of P, does not contain Q. Because of that, by A6 there exists a point on both the line L and the polar of the point, right? And M, which is the polar of the Q. That is, L and M intersect. Okay, that's what I'm trying to highlight. Previously, we established that they are not intersecting. Now they are intersecting. So this is a contradiction. This is a contradiction, right? This is a contradiction. Therefore, once you reach to a contradiction, that's basically the end of your proof. That means what you suppose is not right, right? So oftentimes for beginners, you can make a conclusion, or sometimes we just end it there. So therefore, Q is on the polar of